Welcome to this lecture series on fluid inclusions in minerals, principles, methodology, practice and applications. To begin with, let me tell you that this course is actually meant to popularize this technique of study in geology, which generate very important information and which can be used to understand the various art processes. So, to popularize this and to generate interest among young undergraduate students and the future researchers, so that more number of people use this technique, which this fluid inclusion studies is one of the methodology or technique in geology to understand the art processes which form or modify rocks in different regimes, began about 1.5 centuries ago, and within this time period, starting with very primitive way of generation of information using standard microscopic technique of observation and using very simple device for conducting heating freezing experiments under the microscope, which we call them as microthermometric experiments. Within this time, this technique has improved to a very high level of sophistication with use of many precision analytical equipment, microbeam techniques such as the Raman spectroscopic technique, the laser ablation inductively coupled plasma mass spectrometry like LAICP-MS, and many other sophisticated microbeam techniques like X-ray photon spectroscopy and proton induced X-ray emission spectroscopy. So, all these techniques are being used regularly, routinely in different developed laboratories for characterization of the fluid that we will be discussing through this lecture series. And so, the basic idea is that, and before actually going into the subject of fluid inclusions, how to study them, what kind of information that we are going to generate through this study, what kind of data that we are going to generate, it is important to realize that why, first of all, why we study these fluid inclusions. And to begin with, let me point out that this is a characteristic of the minerals, the constituent minerals in rocks, or the minerals when they are occurring as in the monomineralic form, like say for example, a quartz vein or a calcite vein or situation like that. So, these are not bulk rock properties, these are essentially the individual minerals attribute, and we will through the series of this lecture we will see that how they come into existence under natural conditions. So, the first thing is that before going to understand what these fluid inclusions are, the basic idea is that we are basically trying to understand the fluid. The fluid, as we know, is we are talking about fluid. When we describe the earth, we generally split into two broad components of the earth, as the solid earth and the fluid earth. And many situations where the solid earth and the fluid earth are distinctly separate, like as we know that the fluid earth, the atmosphere which surrounds the surface of the earth, and the hydrosphere constituting the oceans and the flowing river and the stagnant river, the stagnant waters, they constitute the fluid earth which is we see on the surface of the planet, and which is physically distinct from the rest of the earth which is the solid earth. But there is a vast regime in which the fluid is very much in contact with the solid, that means the rocks, and in different depth regions of the earth, starting from the very surface going to the very deep interior of the earth that you can imagine, up to the lower mantle depth almost about 600-700 kilometers, up to depth that kind of a depth range. Also the fluid is present, the presence of the fluid is detected, is understood to be there. And the important aspect is that this fluid actually essentially operates and results in a whole lot of processes. So it's very essential to understand the fluid, to characterize in terms of its constituents, compositions, to understand the physicochemical environment in which the fluid operate. So if you look at the entire spectrum, so this is the fluid which we see on the earth, out of which this is the part which constitutes the saline oceans, which constitute about 97% of it, the fresh water which is 3%, and the out of the fresh water, this is the constitutes the groundwater, the ice cap, and the other water which is about 0.9% of that, and from that surface water which constitutes about 0.3% is the fresh and the saline lakes, which constitute about 87%. This is the fresh surface water, and 11% of it are locked in the swamps, and the river only is 2%. So the situation is that this is the excluding the atmosphere which we just mentioned, the fluid that we see on the earth. We know how this fluid actually shapes the surface of the earth, results in different types of landscapes through erosion, and also such kind of water also give rise to different types of formations, secondary processes, alteration, and generation of new types of rocks and soils on the earth's surface. But a substantial portion of it, and this water is actually has a hydrologic cycle through which it evaporates to the atmosphere and then precipitates in the form of rain, and that is how we understand the natural hydrological cycle which works. Now, if we talk about this water is the water that we presently see, we have fair idea about its compositions, and we can pick them up as samples and analyze. Although this is the water which often, and in many of these instances, which also travels deeper into the earth's crust, interacts with different rocks, and results in different types of phenomena, including sometimes they participate in formation of different types of deposits of metals, which we recover them from different types of ore deposits. And if we as I mentioned that the major part of the fluid is in the earth's interior, and what we see on the surface as oceans and the river water, or the water which is locked, or even the low or the shallow groundwater, almost equal or more in dimension, more in magnitude that much of water is locked in the layers in the subsurface in different types of rocks. If we rocks of the crust and the mantle, if we just have an idea about what these subsurface processes they operate, this is the lithosphere and this is the asthenosphere, which is say up to around 400 about 400 kilometer, and we do have about 600 kilometer, which is the transition zone, and then the lower mantle. What is believed is that possibly the earth's core is possibly devoid of water, maybe during the process that this core formed from the solar nebula. There is no much of water that could get accommodated into the metallic iron metallic core, but almost of the rest of the part of the formation of the earth, this water was initially locked up, initially was present in this deeper region, and it is also believed that during the process of differentiation of the earth, because of the release of these volatiles from the deeper region, actually form the atmosphere, from the ocean. And the atmosphere, and whatever we see, the water which is present in the ocean is also it gets recycled into the deeper part of the lithosphere, and cause sometimes, which is basically the mantle metasomatism. So, it is kind of a recycling of the water which already once was devolatilized or was expelled from the interior part of the earth. During the process of such kind of recycling, during the subduction of the oceanic and the lithosphere into the asthenosphere, they do carry the water and add up to the materials in the mantle, and along with that they do add many of the constituents like the larger and lithophile elements, the more soluble the lighter elements, and the light rare earths, and many of the elements again they enrich this part of the mantle, which becomes an enriched mantle, which is which again gives rise to different rocks by melting, leaves their signature on that. And so, the basic idea of discussing all this thing is that what we know as the fluid, this fluid is majority of its constituent in fraction is actually water, and this water is charged with many types of other soluble constituents, as we can say that water plus various non electrolytes, and then various electrolytes, and this water which is which pervades into the many interior part of the earth, in the lithosphere, in the crust, in the mantle regions, by virtue of the higher pressure and temperature condition, they have a very substantial portion of these various types of non electrolytes, which are our gaseous species like carbon dioxide, methane, sometimes nitrogen, argon, and many of the sulfurous species like these are all they all remain dissolved in substantial quantity in the water, which does a lot of activity and gives rise to a lot of processes. So the spectrum is so wide that this fluid is fluid activity results in very low temperature and pressure regime, such as the very low grade metamorphism that happens in the diagenesis of sedimentary basins when they are just subjected to very low pressure and temperature condition. So, condition as low pressure temperature situations as diagenesis to very high pressure temperature condition situations pertaining to a situation where for the diamond form in some specific part of the upper mantle. So, the range of operation of this fluid is wide, and so they operate in the very wide spectrum of pressure and temperature, and in between lies a whole spectrum of processes such as deposition, such as result of mineral deposits of huge dimension, which are our major contributor of metals, different types of metals. We get them from the different types of mineral deposits which are exposed, which formed in such kind of higher pressure temperature conditions, and this justifies. So, then this fluid that we are talking about, it needs to be well understood and characterized, and we need to retrieve the conditions at which such fluid operated in the interior and gave rise to different types of features, different types of rocks, mineral deposits, and melting of rocks, and so on. So, it is the situation that it is essential that we understand, or that we apply this kind of techniques, which basically to understand the process which is operating in the interior, and the results of the fluid activity, as we have discussed, is pretty okay. So, we know that the fluid activity that we are talking about has been going on since the very beginning of the formation of the earth. So, we can say that this fluid activity has been very much from the Archean to recent. We know there was the ocean was existing, has been existing right from the Archean. With some idea as to how the ocean water evolved, we also have got to know from some other evidence. So, the fluid that we are talking about, essentially we are interested in the paleo fluid. So, that means the fluid which operated in the earth's interior in geological past, in terms of hundreds or thousands of million years or billions of years ago, and we are interested to work out or to retrieve the information as to what was the characteristics of the fluid, what was the physicochemical parameters. So, when we mean physicochemical parameters, we essentially talk about the pressure, temperature, and many other compositional characteristics. So, now the question is that how do we sample the paleo fluid? Are there ways that we could get the samples? So, the most direct way is if we could have the samples of the paleo fluid, we could possibly subject them to all kinds of the studies that we can do in the laboratory and can understand them. So, the answer is yes, we can. Till so far, the way that the subject has been developed, we say that yes, we can sample the paleo fluid. So, where from? So, the paleo fluids which were operating in the different regimes in the crust and the mantle, giving rise to different types of rocks, their constituent minerals. This particular fluid is actually encapsulated or entrapped within the minerals which they gave rise to, and those are those we study them as the materials which you call them as the fluid inclusions, which will constitute the our discussion for the next of the whole of the lecture series. So, these are the fluid inclusions. They are mineral properties. So, we see the fluid inclusions in minerals. So, let us first try to define what they are. So, they are actually tiny fluid filled cavities in minerals trapped during the growth of the host mineral or any time after that. So, we will for the timing we will only be considering where we will keep this we will defer this particular point as any time after for a certain time. So, they are fluid filled cavities. So, when we talk about a fluid, essentially what we mean. So, it could be a liquid, a vapor, gas. So, it could be anything of that, of a combination of that, which we can use a term generalized as fluid. So, it could be a pure liquid or a pure liquid plus its vapor, which could be so whichever condition. As we know, as gas is essentially a supercritical gas which cannot be compressed. So, generally we will be talking about the liquid and liquid plus vapor depending on what the condition was, which get entrapped within the minerals and which you can see them. The thing is that we are saying that they are tiny fluid filled cavities. So, that means they need to be examined with higher magnification and we need to see them under the microscope. They are aliquots of the mother liquor, that means the fluid which is giving rise to the formation of these minerals, which is the mother liquor, that itself will get entrapped within the liquid. They display diverse shapes and have wide range of sizes. So, that is which you are talking about. They can be very small, as low as less than 5 microns to going to centimeter scale, but commonly when we see them under the microscope getting different minerals from different types of rock associations, they generally will be between 10 to 100 microns, and there are very exceptional situations where they can be larger than that, and sometimes even fluid inclusions can be seen in naked eye, and such kind of situations are so exceptional that you can only see them in the museum. Whenever they are encountered, they are seen. They better be preserved in the museum for people to see, and they are distinct by virtue of the contrast in the optical properties of the fluid and the solid host, which we will be just seeing that. So, the fact is that they are small, they are tiny, measuring in just about few tens of microns in their dimension. So, that I will just read out. So, the pioneer in the study of the fluid inclusions along with many. So, the most of the time we refer to H. C. Sorby, who was a mid 19th century European scientist who first started this, who first observed these fluid inclusions in minerals and realized that these minerals, these fluid inclusions could possibly furnish lot of important information, and our basic objective is that whatever information we retrieve from these tiny objects, we until and unless we correlate them to broader art processes and to address issues related to broader art processes. So, Sorby said that yes, and I argue that there is no necessary connection between the size of an object and the value of a fact, and that though these objects have described a minute, the conclusions to be derived from the facts are great. And we over the last 1.5 centuries time, we have realized that what Sorby said is very right. We have generated enough of information on the fluid characteristics in different types of geological environment, then the formation of ores starting from very low grade metamorphism to very high grade ranulite grade metamorphism, and ore deposits of various sizes and various metals, and we have been able to understand those processes and can address fundamental issues of earth processes through the study of these inclusions. Okay, so here are some of the because if we want to know where these fluid inclusions can be found, what kind of materials, it could be possibly infinite, and one has to the kind of information one if you want, one tries to get this information from the what is available in public domain could be enormous, and just I have picked a very small such examples from where the fluid inclusions could be possibly be studied, and we would rather intend to study fluid inclusions in such kind of situation. What we see here, as you can see here, this is just a field photograph from the gold bearing schist belts in Karnataka, the Hattimaske schist belt, and here we can see that within these black rocks, which are the metamorphosed mafic volcanic rocks, which are calling them the metabasalts, within them we could see this white part, which are the quartz veins, and these veins they contain they contain gold. When we go and deeper in the mine, we see that these are the veins which actually are auriferous and they are being mined out for the for gold. This is the same kind of a larger view has been from the exposure scale, where we could see the quartz vein taking a shape because of the way the fluid could just pass through the available open space or available space that the fluid could make through and deposit the quartz. So, the first thing we assume here that this particular process which we see as resulted in formation of this vein is a process which has resulted from the activity of a fluid, and what we are observing at the surface, actually this took place several thousand meters or several kilometers below the surface, where these kind of quartz veins formed as deposition from the fluid which was active during that particular time, irrespective of whatever source the fluid could be. This is an example of it's a kind of a museum specimen where you could see this is a quartz crystal with well developed faces which anybody can identify. This is a quartz crystal, and this also has resulted or being deposited from fluid. And this is one example of one of the rich copper deposit in India from Malanjkhand, and this is the body which is constituting almost entirely of quartz, and these yellow part is basically the copper sulphide, the chalcopyrite ore body. So, these three situations that has been picked up here, that the common thing is that they all are supposed to have been deposited or deformed by the activity of the fluid. So, if we take a sample from this occurrence, and we should be able to see fluid inclusions in them. So, if we just suppose if we want to study fluid inclusion in such kind of a mineral, so what we have to do, we have to prepare a slice or a section which should be about 300 micron in its thickness, because we know that the inclusions will be measuring in tens of microns in their dimension. So, there will be inclusions which will be several such inclusions could be there within this 300 micron thick slice that I have cut out from the samples that I just shown from the exposure, and the only condition is that the surface that I am talking about here has to be very well polished on both the top and the bottom surface. If it is not well polished, if there are surface irregularities, suppose for example, if there are some surface irregularities because of bad polish, and So, when in this case when light, when we are examining them under the transmitted light microscopy. So, when light falls from below, this light will be able to pass through without any problem, and we can get a very good view of the inclusions which will be within this thickness. Whereas, in this case, if light when falls, because of the irregular surface, this light will get scattered, and very small portion of the light will be entering through, and the inclusions which will be there will not get a good view, or will not be able to see them very distinctly within the mineral that we want to see. Okay, so what are the minerals that what minerals generally we see the fluid inclusions? The minerals that we can see the fluid inclusions will be, in fact, theoretically all minerals which deposit from the fluid, but there are certain minerals which will be opaque to the visible range of the electromagnetic light. They will be mostly be our ore minerals, the sulfides and the oxides, which we cannot use for the study of fluid inclusions. So, the minerals which are transparent to the visible part of the electromagnetic spectrum can be used to see the fluid inclusions. So, these transparent minerals could be, the majority of the inclusions that we study are in quartz. There could be calcite, fluorite, apatite, kind of mineral species which you can see these inclusions. There are metamorphic minerals like even garnet, cordierite, which can be used for examination of these fluid inclusions in them. So, in a way, and going up to the, as I mentioned, that even you can see fluid inclusions in diamonds. So, the spectrum, the range, the different types of minerals that you can see fluid inclusions are quite a lot, and we will be discussing them in the course of this lecture. We will see how inclusions are occurring in all these types of minerals that we are talking about. And so, just have a quick look as to what these minerals, how the fluid inclusions they look like in transmitted light microscopy, and we will continue discussing about this in the next class. Thank you.